This demonstration will show a conduction problem with multiple layers where the inner layer is generating heat. The upper plate is exposed to radiation and the maximum temperature is located at the outer surface. Furthermore, the ambient temperature and lower surface temperature are given. Both sides of the multilayer wall are losing heat due to convection. In the first question, we are asked to derive an expression for the temperature profile in the reactive layer. To do so, the heat conduction equation should be derived and solved by use of the boundary conditions. To derive the heat conduction equation, we should set up the energy balance for an infinitesimal element within the reactive layer. The general energy balance for those systems includes the transient term, heat fluxes due to conduction, and the heat that is generated within the element. But first, we'll start with sketching the energy balance. So the infinitesimal element is drawn like a 1D element located within the reactive layer. Heat is conducted inwards, but at the same time it is being conducted outwards as well. Furthermore, we have heat generation within the infinitesimal element, and we are searching for the steady state temperature profile. So we're not dealing with any change in internal energy over the course of time, which yields the following energy balance. Then we get to the second step, which is finding an expression for these terms within the balance. The incoming heat by conduction can be expressed by use of Fourier's law, where the outgoing conductive flux can be approximated by use of the Taylor series expansion, as we are dealing with a sufficiently small domain, where filling in the ingoing conductive flux yields this expression. Lastly, we have to define the heat generation, which equals the volume-specific source term multiplied with the volume of the infinitesimal element. Having defined these terms, we can put them into the energy balance and do some rewriting, which yields the conduction equation. Having found the conduction equation, it can be solved by use of the boundary conditions for the given domain, which is the reactive layer in our case. We need two boundary conditions as the temperature has been differentiated twice with respect to x. The first boundary condition we try to find is the temperature gradient at x equals 0. We'll do this by setting up an energy balance around the lower plate, where the domain for this balance looks like this. We will use the convention of heat moving into the positive x direction for now, so heat will enter due to convection and it will leave due to conduction, which gives this energy balance. We know expressions for these fluxes, which yield from Newton's law of cooling and Fourier's law. Note that the negative signs account for the direction of the heat flow. Some further rewriting yields the first boundary condition. For the second boundary condition, we will try to find a temperature at x equals 0. Again, we will use the energy balance around the lower plate, but this time we will use a different definition for the conductive flux. The convective flux can be defined by Newton's law of cooling, where we take into account the direction of the heat flow, where the conductive flux can be written by defining the gradient by use of the temperature difference at both sides of the lower plate over its thickness. We can do this because the profile has a linear behavior. And then some further rewriting yields the second boundary condition, which is the temperature at x equals 0. Now we have two boundary conditions and we can start solving the conduction equation. So integrating once yields this expression, and we can already use the first boundary condition to find the expression for integration constant a, where all terms with 0 cancel out, which gives us the constant a. Then we can integrate once more and use the second boundary condition to find constant b. Again, all terms with 0 cancel out, which yields the following expression for constant b. And if we substitute the found expressions for constants a and b and do some further rewriting, we will find the temperature profile of the reactive layer as a function of x. In the second question, we are asked to draw the temperature profile for all plates and its surrounding. We know that all temperatures will lie in the range of Tmax and Ta. Far enough away from the plates, the ambient will equal the temperature Ta. The upper plate surface is equal to Tmax, and when moving from the left to the right, the temperatures at the interfaces will decrease. We don't know the exact temperature drops, but since the upper plate has the highest conductivity and the lower plate the smallest, it makes sense that the drop will increase per layer. In the left layer, the temperature difference is almost negligible, which is often the case for materials with high conductivity such as aluminum. It helps to first draw the slopes of the profile at the different points. For the left side, we know that the slope should be horizontal, which is a characteristic for profiles in fluids where convection is happening. At the interface between the solid and the fluid will have the steepest slope, as in general those have lower thermal conductivities than solids. At the interface between the two solids, the left layer its slope will be less steep due to its higher thermal conductivity. This is also the case for the other interface between the two solids. And again, we have a solid fluid interface where the fluid will have the steepest slope due to a low thermal conductivity. And finally, we will end with a horizontal slope again. Then we can start drawing the profiles, where for the left side we have an increase in slope when we move closer to the interface, which is because convection becomes more significant. The first layer will have a linear behavior as we have conduction through a flat plate without any sources. The second layer will have a steeper slope when moving from left to right. This is because heat is generated, so more heat is conducted. From Fourier's law, you can see that if more heat is conducted, and if the conductivity and area remain constant, the gradient should increase. The third plate will have a linear behavior as well, as we have conduction through a flat plate without any sources. And lastly, for the surroundings, the gradient should be the steepest near the interface, as over there convection is the most significant. So in short, this demonstration showed how to derive and draw the temperature profile in cases where heat is generated as well.